All right, just to catch everybody up just a little bit, the first thing you have to do is create your account on Brev, and that's going to give you access to our org over on, that's how you're going to get access to GPUs. We have two parts to this tutorial. So one of them is going to be the kernel authoring portion, which I'm going to lead. But the second part of it is on deployment, and Natty is going to lead that one. Because it takes a bit for the Launchable to spin up for the kernel portion, we want to use every single second we possibly can that we have with you. So we're going to kick off with the deployment piece first, because that one goes a lot faster. But we'll warn you when it's the right time to go ahead and kick off that, that instance for the kernel writing portion. So that it'll take about 15 minutes for it to spin up. So we'll just try to use that time as best as possible.
Quick question, does everyone already have an account? Is that a yes? Do you raise your hand?
Yes.
Oh, okay, good.
If you need help, just raise your hands.
Yeah, if you need
three
help,
TAs
we have,
here,
like,
we're here to help.
Jaya to help. In the meantime, just before we get started, I'm just gonna quickly intro myself. Okay. I'm Nati Clementi. I am a software engineer at NVIDIA, and I work for the Rapids Cloud Deployment team, where basically what we do is everywhere in the cloud that there is a GPU, we'll try to find a way of getting all the Rapids ecosystem running in there. The Rapids ecosystem is Python libraries to do data science and machine learning and other stuff using GPUs in a very Pythonic way. We're going to see a little hint of that, but we're not going to concentrate fully on that. Today, what we're going to go for the first time of this tutorial is try to answer the question of, hey, I have access to a GPU. How do I install things in there? How do I get things to work in there?
I'll try doing the...
So just again, if anyone hasn't created an account, this is the link. Go there and create it. So before we kind of get going, a quick show of hands. Who has ever run code on a GPU? Okay, more than 2/3 of the show. Who has ever installed GPU packages, drivers, or tried to install something on a GPU? Okay, maybe half of you. How many of you write Python day to day for work or stuff? Okay, pretty much the whole room. How many of you uses pip or a combination of UV pip? Okay, does any of you uses Conda? Okay, you use both. The reason why I ask this is because during this tutorial, we're going to show you how to install things like with UV and pip, or just pip and Conda. We can spend time showing you both, or I can spend time on, let's say, one of your choices, and maybe go a little bit into, if the time permits, into showing how to use some of the performance and debugging tools. So this is a question for you all. Would you prefer to see how do we deploy things and install things both ways with UV and pip and Conda, or would you rather choose one, which we can kind of go into now, and maybe see a little bit of tools that are for debugging and things like that? Okay, who wants to see both UV, pip, and Conda deployment, and then maybe kind of stop there? For the record, a full version of this tutorial with all the rest of the content is going to be taught tomorrow at PyData Global, and it's going to be recorded online. So if you say, okay, we can see that later, then we can concentrate today on all the installation parts. I need you all to be loud and clear now. What would you like to do?
Both.
Can you
Both.
maybe both? Okay.
I'd rather just UV or pip or just one.
Okay. So we have some people that rather do one, some people that rather do both.
Both.
Both? Okay. Who wants to see both? Raise your hands. We got 2 people. Who would rather to see just UV pip? Okay. I would say that's the majority. So we're going to see that. The instructions are going to be there. And then again, like, there's going to be a recording probably next week or so after PyData Global on that. All right. So if you all have your account, I'm going to give you where the content is, although I'm going to be typing most of it on the terminal. So if you go, just for the sake of it, I think I can copy this link because I don't have it. OK. That's the full-on tutorial here. I'm going to make this way bigger. Is that big enough? Maybe even bigger. The Accelerated Computing Hub is like a place where we have so much content about GPUs, and everything is usable. Katrina has led the effort on this, so big kudos to Katrina to putting all this effort on. We have so much content that you can kind of later on go and explore. Right now, we are going to concentrate on what's on tutorials and the one that says GPU deployment from scratch. This is just a markdown file that has a guide to go and do all the things that we're going to do. But right now, if you're all in Brev, so you should see something like this, if I make it bigger. Make sure that you're under the 2025 PyData Boston organization spot. Is anyone not in there? Raise your hand now. Cool, everyone's in there. So we're going to go and then create a new instance. And please here go and find the ones that says L4. I know there is tempting, there is like so many big machines and stuff. Please just don't go and grab an H100 or things like that. We're going to be doing smaller things, so be mindful that you're having free credits. And we're going to choose the one that is a GCP instance. Don't choose an AWS one. At the moment, those ones have like a known issue. So choose a GCP instance, and then click on there. And then you can give them any name. I'm going to say PyData Boston GPU deployment. You can put the name, any name that you want, and hit on deploy. This should take like not too long if things work.
Is it okay if they choose a different provider other than GCP?
So
I just clicked the default, sorry.
I mean, if you can close it, try. I know that things on GCP work. On AWS, they were not working. So for some reason, I'm not being able to see. This one, it says deploy, and it's not kicking. So that's not great. All right. While this deploys, I already have this installed. You should have the instructions here on how to install the CLI on your laptop. So go ahead and do the brew. If you're on Mac, it will be brew install brepdev conbrep. That just copy that one, and then follow the instructions in there to do the brev login, and then the brev shell PyData Boston. So. Okay, so I'm gonna do brev login. This is still super small, so.
Yeah, just hit that.
Sure, like maybe.
I think, yeah. Scroll this.
So you should see things like this.
Oh, I can't do this.
Just choose a name. That's pretty much it. It's a little bit finicky, but it works.
This one is still running. And I need to make sure that you set, if you only have one organization, you should be able to see it already set for that. In my case, I need to switch that. So it's 2025.
So after I came here, I just
Rep set 2025.
I'm not sure my laptop like Microsoft does.
Okay, has anyone been able to like do the Brev CLI install and then the login? you probably don't have the instance running yet. That's fine.
No, like logging where?
Who is stuck?
I'm stuck.
All right. Can you help? All right. Is anyone about to this point? This one's still building. Okay. This one, it says it's running the VM. I think I might be able already to, before it kicks. It's missing some like UX, UI stuff, but like I think we should be able to get into there. So you should have, after you did the Brev login, you should be able to copy this command in your terminal, and then we're going to be inside the instance. Here in my case, it's PyData boss, and in your case, should say whatever name you put to your instance. So I'm going to copy that, and then I'm going to paste it there.
No, it's built.
Okay, so it's not ready. So it says waiting for the instance to be ready. This is taking longer than what it used to. There we go. We're in. All right. Can I get a show of hands of who is in their instance? Great. 2, 3, 4, 5, 6. Who's 6? 7. Okay. Where is everyone else stuck? Not stuck, just catching up. All right. So in the meantime, what we're going to see is, so right now, just a quick question. Is this big enough, or we need to be bigger? A little bigger. All right. There, I guess. We type. Cool. All right. So up to this point, we're here. We are in an instance. The instance has a GPU, or at least that's what we were told. And when we click on the stuff, what we're going to do is kind of like start looking into some things and to confirm that we do have the GPU, and then we're going to try to install some stuff and then see what happens. For the big chunk of this, we're just going to be using a terminal and then installing some stuff. Brev has some particular things when we move into Jupyter at some point that might be slightly different for some people. But for now, it's like, this is the equivalent of, I went to, let's say, GCP, AWS, Azure. I got an instance with a GPU. What do I do now? So the first thing that we can do to confirm that, that we have something is like exploring our, what's it called? Sorry, I'm going to put my glasses because I realize that I'm old now, so I don't see that well. So the first thing that we want to do is like maybe check what kind of OS do we have. So we're going to do cut and then just check EDS, OS, release. And then this is also going to tell us a couple of things that will be useful when we are installing things later on. Sorry, there's someone over here. So we're on an Ubuntu 22.04 LTS. That's pretty much the main info that we need when we're going to be installing kind of a couple stuff. So the next things that we want to do is, okay, check what kind of GPU do we have and then what are we running. So we're going to do NVIDIA SMI. And then here we see is like, okay, we do have an L4. And right now we're not doing anything. We do have a CUDA version of 12.8. All right, so up to here, the thing that we know is that we do have a GPU. Then let's check if we have something that allows us to install things. So let's check if we have pip. Okay, we do have the system one. So this could say, okay, well, we do have pip. Most of you have used pip. Let's just try to install something and then see what happens. So one of the things that we can install is, let's say, CuPy. CuPy is, who has ever used NumPy here? Okay, more than pretty much everyone. CuPy is, if you can imagine, is like the NumPy version for GPUs, right? So, and it's still super Pythonic and stuff. So we're gonna just try to install that and then see what happens. So we can do pip install, and then we need to tell them that it uses CUDA 12. So in this case, we're gonna do CUDA 12x. So it's one, it will just search which one is the CUDA 12 version that it has. So if we do that enter, then should install some things. We're seeing install collected packages, and there. So now let's just try to use CuPy, right? So we're gonna do in this case, I think is because we haven't like kind of symbolic link or set up which Python, we're gonna have to type like Python 3, but just to get oh, I forgot that we cannot do clear in this. All right, so let's try to import CuPy and do something. So we do import CuPy as CP, and then we can, let's define just a GPU array, oops, X GPU. It's gonna be cp.array, and then something simple like 1, 2, 3. And now, okay, we had a GPU array, and let's just try to square it and see what happens. And then it says underscore GPU, and we're going to do square it. And it didn't work. Any ideas why this didn't work? You don't have to know. I mean, it says it right there, but like, if I read this, it says CUPL failed to load lib nvrtcso, blah, 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 OS error, cannot open share. Okay, you have an idea. What's happening?
No CUDA installed?
CUDA is there. We saw that there was CUDA 12.
One of the other stuff you install on top of CUDA.
Okay, yes. So what's happening here is pip, when we install things with pip, it doesn't, GPU stuff with pip, it doesn't bring, at least not for all the libraries. Some of them are catching up, and this is getting way better. And for the record, this CuPy error is not going to happen soon. Like in the upcoming 1 or 2 releases, this is not going to be a problem. But up to now is like, when we install things with pip, we cannot bring everything that we need to make sure that things run. So what this error is telling us here is it's looking for this lib nvrtcso. That's the NVIDIA runtime compiler for CUDA 12. And it's not installed or not on the system library path, so it's not finding it, it's not there. And this is like what is used to just-in-time compile CUDA at runtime. So when we are doing the square of this array, CUPA needs this library to be able to dynamically compile things on the GPU and then run it. So what we need to do is just check that we have the core CUDA libraries in there, so then we can go and then install stuff. So we're going to exit this, Control-D, clear stuff, and then we are going to check what do we have. So if we do ls -ld and user CUDA, well, no, it's user local CUDA, and I think we're going to check for whatever we have here. Okay, so cannot access no such a file or directory. So because this is missing, we need to install this. So if we want to install packages with pip or UV-pip at some point, you have to make sure that you have the CUDA runtime installed on your system. If you were to be using just Conda, this won't be a problem for you. Conda has allows you to kind of package binaries, and then so the CUDA runtime could be packaged there, so then we can bring everything. Also in the future, I think up to now, CUDF and QML are being able to kind of install things like just via pip, but some other libraries and some dependencies of them still needs this to be at the system level, so we need to make sure that we do that. So to be able to do this, we need to be able to add like CUDA to our system, the CUDA runtime. So this part, I'm going to go to the Markdown file and copy because it's a really long link. But go to Is everyone in this guide? Or if you're not, type go to there. You can take the QR code, but then in the phone, you're not going to be able to link it. So look for GitHub Accelerated Computing Hub.
Yeah, it's under the NVIDIA space in GitHub. So github.com/NVIDIA and then accelerated-computing-hub.
I'm going to wait until everyone is there.
This is our open education repository that we put a lot of materials in there. And so, yeah, instructions for this one will be in there as well.
All right, so is everyone in there? Can I get a thumbs up? 1, 2, 3, 4, 5. Okay, great. So once we're here, I'm going to go back so then people see it. Under tutorials, so you're going to go to tutorials, and then GPU deployment. And then in there, yes?
Oh, can you please go back to that website?
This one?
The GitHub one?
You want the slide?
Yeah.
I can make, this one is big enough, but it doesn't allow me to make it bigger. So if you Google GitHub Accelerated Computing Hub, that will be the first link that shows. All right, so in there, under tutorials, under GPU deployment, there is a GPU deployment from scratch. And then we're going to go to the section that says Python software down here. I think I passed it. There. So we're going to copy this. This is that add the NVIDIA apt repo. So basically what we're going to do is we have to select the one that matches the specific OS. That's why we check the OS at the beginning. This one is already written for the OS that we have in that instance. So you should be able to just copy that and then paste it in here. Okay, that copy way too much stuff, but let's see if that works. Yeah, that will do. All right, and then hit enter. This will take a few seconds. Shouldn't be that long. Is anyone stuck? No, this is going? Okay, good. Good, good. All right. Should be up to this point. Does anyone have any questions? Yes?
Can you put the pip commands back up?
The ones that we saw before? Yes. We can find it. Those should be in here. You want these ones that we were checking before? That should be the part that also fails. Okay, let's see where we are. Okay, this is still installing, but you say this is the key, right? Over, whoops, it moved. But you will see this guy. This is the guy that we were missing. Among all the other stuff that this guy needs.
I think we need to install this one.
All right, so taking a little longer than what I wanted. It's getting there.
And this is the same pip install as the other one?
No, this is, so after the pip install stuff fails, so.
Didn't fail?
Did you did this already?
No.
So you're telling me that you did pip install stuff, the CUPI, and then when you run this code, it didn't fail?
Oh, I didn't run the code. No.
Yeah, do you have a question?
Where is that in the?
So in the repo, so in here, if you go to there,
Yeah.
and then you go to tutorials, there's a folder tutorials, and there's one that called GPU deployment. there is a markdown file in there that has all these instructions.
Which command you currently running?
Sorry, what?
Which command you currently running?
Oh, so we, after we got the fail, copy this. It's under the pip install. It says add the NVIDIA app repo. So we are running there. So what we're doing now is like adding the repo to be able to install the CUDA toolkit.
But you said we have CUDA installed.
We have CUDA, but not the CUDA toolkit installed. So we have like basic system stuff, but we're still needing like some stuff for the Python things to install. So remember, like we got this error that said this guy. This is the guy that we're missing, and that's on the CUDA toolkit.
So toolkit versus CUDA there's this distinction.
Yeah, there's like different levels and different layers of package. All right, so let's check if that is done. Okay, it's still going. That's so weird.
Yeah.
Well, it used to be faster. Come on.
Virtual machine.
So I'm running this terminal here, and I'm doing the pip install on PyData, and then I have a Jupyter instance, and then it's not PyData.
Yeah, I think that's like AWS or GCP where you have everything installed. And then you just use it.
Has this finished for anyone, or everyone's still going? No?
It's still going.
If for someone finished, go ahead and the next step is to install, whoops, I went way too ahead. This command, the one that says sudo apt-get -y install CUDA toolkit 12.8. If for anyone has finished, actually that run all together. That's why it's taking longer, my bad. All of this is running, so we just gotta wait. Should be done soon.
It does have it.
Has anyone ever like had issues like this, or like trying to install things and then things hasn't worked? It's like while we wait for this, it's like, and I'm just thinking in terms of like writing content and stuff like that. It's like, was it hard for you to figure out what you needed to do? How do you find solutions? What do you wish it existed? And don't say LLMs, because that, well, yeah, that makes it easier. But let's say if you didn't have that, or like, how were you able to find help, or what do you wish it existed?
To better have the all dependencies in the one package.
Okay, so they say,
Yeah,
I just want to install things and not have to worry about.
Yeah.
Okay.
Or sometimes, I mean, it can depend on the system that you're on, like how you get those dependencies. Like just a complete inventory of those dependencies alone is super helpful.
All right, so having like, let's say, how do I install things if I'm on, I don't know, Rocky Linux or Ubuntu or things like that? Having more detailed instructions.
I'm thinking more like C++ development or something Python. So.
Oh, okay, fair.
Also, if it's the vulnerability within the package, how quickly it will be fixed,
Okay,
usually.
that's
Yeah, so because if it's the restricted environment and it's flagged, we can't use it. And so the main pain for using the Python packages is to have a quick fix, a new version.
Okay. Cool. Thanks. Yeah, I'll take note of that. Okay. So we have things installed now. And basically, now we should be able to run the code that we ran before and then not have this issue. So let's just try that again. If we do Python 3, we can just arrow up. So we can import CuPy. We can generate our array. And if I'm not wrong, I should be able to run this, and things should work. And then nothing broke. So I mean, we can check this, but and we do have the square there. And yeah, up to now, it's a super simple example, but it means that okay, now we got the things in there, we got the system in there. Let's try now to we can install like other packages. And one of the things that we could do is install QDF. That's like the other, oops, Control D, Control C. Yes, I want to exit. But since most of you were interested on installing things with UV, so let's just like jump ahead and then do that. Also, I just want to be mindful of time. So to be able to do that, we need to get UV in our things. Like if I do which UV, and like, oh, for some reason UV is here, but that wasn't there before. So since it's there, well, just might try to do something with it, because last time that I did this wasn't there. So I just want to know, let's, just in case, let's pretend that it's not there, so we can.
I don't see it.
You don't see it?
I don't see it.
Okay, so we are just gonna pretend that it's not there and install it if it wasn't there, since some people don't have it there. So if we go to our notes, you will see under the UV section, we need to get UV there. So we can curl it from the Astral site. So we're going to copy this command, the one that says curl dash LSSF and stuff. So we're going to get that there. And then we're just going to install. So, hey, everything is installed. In my case, it seems like it was there. So I don't know why in some cases it's there and in other ones it isn't. But just in case, if you didn't have it and you're installing it, then you're going to source your bash RC. We need to just kind of like say, hey, use this. And then we're going to create like an environment. Just to not mess up with like what I have in here, so there's nothing in here just by the CUDA keyring. I'm going to create a folder, okay, there, sandbox, I'm going to call it. And then in there, on a CD, and we're going to create a UV environment. So we're going to do UV VM, and I'm just going to do dash, I think it's dash, I don't remember, yeah, dash dash, Python 312, I think that's dash dash Python, and then 312. Probably should work with 313 just to make sure. I know things work with the 312, so we're going to do that.
Oh, okay.
And then it says, okay, create a virtual environment. This is how we activate it. All right, copy that. We activate that environment. And up to this point, I only have Python 312 in there, but I would like to install some stuff. So we're going to install QDF. So we're going to do UV pip install. And we're going to do in between quotes QDF. We need to tell them which CUDA version. So that will be Q12. And equals, and this is the latest release that we have. So it's 2510, and there might be something. So we're going to install that. There's like a bunch of packages in there. You see this one like comes with MBRTC. So QDF is one. Yeah.
I'm sorry, what was the version again?
Yeah, I'll get you that in a second. There. Is QDF dash Q12 equals 2510 asterisk. Cool. So one of the things, do you use UV like for your preferred installation packages these days with Python? Okay, what do you usually use?
Whatever's available in this environment.
Okay.
Or whatever.
Fair.
Sometimes it's just
whatever is available in there. So I know like UV has become like very, very popular, and it's very, very fast. One of the drawbacks that UV has is when it's a kind of like an important limitation if you're like a person that likes working with nightly releases or pre-releases. Unfortunately for UV is an all or nothing on pre-releases. So that might mean that, oh, well, maybe if you want to install, let's say, the QDF nightly version, which is like before the stable release goes out, that means that it's going to install, you have to tell it to install it, but it will also install everything nightly for everything else. And we can't guarantee that all the other stuff works. So if like you are a person that is available to work on the leading edge of the package and wants to experiment with that, just have to be mindful that we can't guarantee that all the other packages are going to be working compatibly with the latest of the latest. So if that is your case, I will be like, maybe just use Conda. Conda will allow you to do that like in a safer way. But that's like a very, very edge case or a small limitation, like if you're in that end. So, so that's kind of how we do things with UV. I would say we do have 15 more minutes. I can either go and maybe show you a little bit of how to use some of the debugging tools, and then like the Conda people can go there later on and then check on that. Would people prefer to do that, or would prefer to kind of go through Conda instructions?
Let's see Conda instructions.
You want to see Conda instructions? Okay. So right, so we can see that. But since we are like at a good point, I would like to just make a short pause. Go to Brev, because we're going to kind of hit started the next part. So we're going to launch now what we're going to need for the next part of the tutorial. So in here, when you're in Brev, you should see under Launchables, there is one in here that says PyData Boston right there. So click on Launchables.
One quick note. So by default, this launchable is using Crusoe as a provider. If you find that there are no GPUs available with Crusoe, or if you get an error message indicating that, go ahead, click View All Resources, and stick to the same GPU, the L40S, but switch to AWS. Find an AWS instance and switch to that, okay? So try Crusoe. If there are not enough resources on Crusoe, switch to AWS.
And for that is like to be able to try it, go and then like where it says deploy Launchable, hit that. I'm gonna
come around to make sure everyone has their Launchable set up.
Exactly.
Oh, yeah.
right.
No, like I thought, I'm like, why are we waiting around if I sell them?
Has everyone been able to kind of hit the deploy Launchable and not get an error, get something going on?
Yeah, so you don't have to worry about this right now for the
Good?
next part of the
Okay,
course.
great.
Okay.
Yeah, exactly.
Do you need help?
Yeah,
Yeah.
Are you okay? Did you deploy the
so,
module?
I can't get to that screen, so.
Oh, you don't have to do anything.
You cannot get to
Take
the
some
screen.
time.
Okay, so in Brev,
Oh, no. Oh,
do you know,
PyData Boston.
yeah, and then in Launchables, and then hit it, the green stuff that says PyData Boston at the bottom.
And you don't have to worry about this right now. Just,
Yeah, it says
in about
click there,
2 minutes we'll get to it. Are you
and
okay?
then you should be able to get to this page.
And deploy.
And deploy. And if the Crusoe instance doesn't get people deploy,
It's there, the Crusoe is there.
is there? Yeah, well, so do deploy Launchable.
And when it's ready, this open notebook piece is going to start working and go in there.
Yeah.
How you doing?
All right. Is everyone have something going on the back?
You're good.
All right. You need help?
Open notebook.
Okay, great. So now we're going to go back to our terminal. And
I like just.
let's see
Okay.
what we have here. So
Form the next part.
in this case, just to kind of check the UV installation,
But till then, you guys.
we are just going to open the Python interpreter. So now we are on this like sandbox environment, right? So I have Python there. I don't have to do the Python 3 because I'm like on UV, nice stuff. And we just installed CUDA. So just a glimpse. CUDA is this library that allows you to do everything that Pandas does, but on the GPU. There's like there are like a couple of great tutorials about using CUDF, as well as also like, hey, I have just pandas code, and I would like to see if this will run on the GPU. You can run it with just literally one flag, and it will automatically run on the GPU for you, or you can profile it too. We're not going to be seeing any of that today, but in the accelerated computing hub, there's material in there, and if not, I can also like kind of point you to some other material if you're interested in that kind of application. So in here, we're just going to do import CUDF, and then it's taking a bit. We're just going to like copy the commands that we have here, so we don't have to like kind of type it all. But we're going to create a data frame, and we're going to do some operation. So
Go ahead and click on that.
paste.
And then when it's ready.
And then you'll say, well, this is fast and stuff. Like, how do I know that it runs on the GPU? It is running. You're going to have to believe me. But if not, one of the things that we could do is I think, well, not in this case, but you can profile code and then check the stuff. As part of like this tutorial, there is like more content on profiling and then looking into the data and looking into the stuff on what's happening. But like for this part, we're just going to limit to the installation portion and then move on into the CUDA kernels in a little bit. So we know like kind of things working here. We're going to deactivate this environment and then show the Conda version things, and then we're going to move on into the next section of the tutorial. So we're going to hit deactivate, and we're going to get out of this like folder. So we're like back into just the main terminal. So to be able to use Conda, we are going to rely on MiniForge. MiniForge is like a small Conda Forge distribution that will have all the stuff that we need to have. So, and we know that like Conda will bring kind of like all the things that we need. So to do that, we go back to our cheat sheet, and then we're going to copy this command. So this command is kind of installing MiniForge, and then is making sure that we have the things that we need to be able to install things with Conda. So we copy this, and then we literally just paste that there. There's not much magic. Like in this case, we're just like literally installing MiniForge, so we can use that as a package manager. Yep.
All of this convinces me that like I'm gonna have a really hard time deploying code to NVIDIA. How do you recommend we actually do it when we want to deploy the production app?
So what do you mean by deploying code to NVIDIA? Do you mean like deploying or installing things on a GPU?
I want to run Python code on an NVIDIA GPU someplace. And it looks like there are a lot of pitfalls. What is your preferred best practice way of doing this?
Yeah, so I think there are like two parts of that question. What is my preferred part? That will be going via Conda. Like Conda in this case, we wouldn't need to do like the installation of the CUDA toolkit and stuff, like, and then like things will like, we will just literally install MiniForge, which is because the instance wouldn't have it. Most instances will have it, and then install it. Now, sometimes that's not something that you can do. Let's say that you're given a system and you have to work with what it's there. Like if you have the option of setting up your system, I would go for Conda, because it will make, like, especially if you're like on the data science ML world, that will make like your life easier. Now, if you tell me, hey, the DevOps that gave me the instance only gave me UV pip, well, then you kind of have to go and then manage all those stuff. That being said, is some of these caveats are particularly to some libraries, and that is evolving towards a place that is going to be more like Conda. So you wouldn't have to do all this like, oh, I need to install this part and this part from here and this part from there. It's just like it's pip wheels are evolving towards getting to that point. It's just kind of catching up. So for example, if you were only to need CUDF and QML, you wouldn't need to install like the CUDA toolkit part and stuff. That will already come with the pip wheel. But in some situations, you need like kind of having that extra. Does that answer your question?
Should I use UV or pip? Yes, it does.
Sorry, like UV and pip are kind of like the same.
No, if I should use UV and pip or conda.
Yeah.
It answers that question, yes.
Yep. But sometimes it's like, yeah, you don't have like the option. So, yeah, please enter. Yeah, sure. Now why is it asking me to do this? I don't want to accept that. Okay, so if I do source, now that dot bash rc, then now we should be able to kind of create an environment. So we're going to copy what we have here. This will create an environment through Conda4 that has like CUDF, and we'll tell it to use the CUDA version between 12.0 and 12.9. So we're going to do that. And then we're activated afterwards. Okay, this is because it didn't accept the terms and services. They shouldn't ask me to accept the terms and services. This is kind of new. So we're going to try to do that again. Please review the license. Sure. Okay. We're going to do this for now, but they shouldn't ask me that because I'm not using Anaconda. So enter.
We're always the experts. Just tell us, like, just use conda if you
yes.
like, that's fine.
All right, so now I should have Conda. I need to do the source. So we'll source our bash RC. And now I'm on the base environment. All right, so if I do which Conda, I should have Conda in there. So now it's like installing a package or creating an environment. We can copy it from the from our notes. So we're going to do this. And this will be like going back to the questions that he had. We saw Conda at the end, but like if we wouldn't seen Conda at the beginning, we wouldn't need to do all the caveats of kind of going through the ports and saying, oh, I need to install the sudo apt-get thing via to be able to get kind of like the parts of the CUDA stuff that it didn't have. So that will be that. So we're just going to install a bunch of packages.
No. So
and then
we make it a point. It's complete.
If anyone has ever worked with Conda, then the later step will be to kind of Conda activate that environment. And then we will be able to do things immediately.
And so you'll see that we've organized it, right? There's a PyTorch container, there's a CUDA container, right?
Like the other, I would say also the other advantage of working with Conda, like in my experience, Conda is better at like kind of handling kind of cross dependencies and things like that. Like if you have an environment that has a couple things installed and then you keep pip installing things on top, it will install them and it might break things that you have. Let's say that you have a package that depends on package A version 1, and you install a new package that depends on package A version 2, it will install it and upgrade that version, meaning that it might break your other package. Conda will tell you, hey, these two don't work together, you need to downgrade, you need to do things, and it will be more vocal about those stuff. Yep.
You can also do the pip compile, and it will tell you the same.
Yeah, but like it's like as a like if you are like more of like a user just getting it started and you're not aware of that, is that it will install it and then oh shoot, now my environment is messed up, and it won't like kind of stop you to doing that. So
you know, like what?
Yeah, so I would ask.
But it has like not everyone has access to everything, so it's good to know like all the options that we have.
Oh, yeah.
So in this case, we just like activate the environment that we created. And then in here, we should be able to do again something like import CUDA, because we just install it. And then we can do s equals CUDA series, something simple just to show that we install things. A,
Go to launchables, click on this PyData.
and
That's the one that we
let's say B, so this is just a simple series. And then we can do s dot apply. We can just apply the function lambda x
when you click on that.
len of x. This is just like a simple thing, but it's just doing that. So there are like plenty of more stuff to see and then go over. I think like the next part of this series is like very interesting in terms of like it will teach people how to go into, am I running things on the GPU? How do I make sure that things run on the GPU? What are the tools? We're going to stop right here. All of this is available still on the markdown that I gave you if you want to keep exploring it later on. But right now, we're going to move on into like another part. We're going to get to play with CUDA kernels on a notebook and then see a couple of things. So one of the things that I will ask you is that you exit the connection, and then when you go to Brev, which is somewhere here, at some point you should have under GPUs, you should have your instance. We're moving to a different instance now, so please be mindful, and then you can kind of like shut this one down or stop it and shut it down. You can launch it maybe later today if you're interested. But I'm just going to stop this one.
Yeah. Don't shut down the one that you just started for
Yes,
the second part.
don't shut that one
Don't shut down the one that has the name of the launchable, which is the PyData Boston one that you clicked on.
So I did not start one, but you should all have in the launchables one, or actually under GPU, there should be one that is the launchables in there. Katrina, do you want to? You have probably like one in there.
Yeah,
So.
Switch off.
So, part 2, yay. Now that we've thoroughly confused you on this deployment, I'm just kidding, now you know everything about deployment. Next part of the tutorial, we actually already have the environment all set up for you, so we're gonna move into a notebook environment. So if you haven't done this already, go into Launchables and you're gonna see a PyData Boston 2025 launchable here. If you click on that, deploy the launchable here, and then it's going to create an instance. And if you go to your instances, okay, that's awesome.
Yeah, I think go back.
Hang on a second, I'm sorry. They keep changing our UI a little bit, and so I apologize if I get a little. So you're gonna see this PyData Boston launchable that started. So I already started mine. And then this Access Notebooks button, either on the instance page or here under your GPUs, when it's ready, it's gonna start kind of glowing like this. Click on it, and it's gonna take you here. So you'll see this, and this is the second part of the tutorial.
Is everyone there?
So who has reached this page already? Just by show of hands.
Cool.
And others who are not raising their hands, are you waiting for your launchable to deploy? Okay.
See, this is there, but then I don't see the.
Want to collapse?
Yeah, I'm like, what did I, there we go. Okay.
Want to make it a little bigger?
Wait for this to finish building, and then eventually you'll see the open notebook. Anyone else having issues with opening the notebook?
Do you deploy?
I deploy it, but
Okay,
but it's
Okay,
not.
so hopefully you have your first instance has been shut down and everything. This is opening a second instance, and we have everything all set up. Everything is already installed. And so this is the part where we're going to move into kernel writing. We thought that we'd change the order a little bit just because, you know, as you can see, it takes a bit of time for this to spin up, and we were trying to be efficient with our time. But this is kind of what I think was mostly in our description, to talk a little bit about CUDA Python. Let's talk a little bit about, you know, how to write kernels, how to use your GPU efficiently, and kind of understanding some of the fundamentals of CUDA. And the thing that I really want to stress in this whole thing is that we are going to go into a great deal of detail, and it probably will get a little confusing. But the thing to take away from this is really the CUDA programming and execution model. If you understand how CUDA works, CUDA is universal to all of NVIDIA, okay? So most things are built on top of CUDA. And so if you understand CUDA, those concepts don't change no matter where you're accessing it from. So whether you're using a low-level library, or you're using Rapids, or even PyTorch, the concepts are the same, the vocabulary is the same. And so you'll be able to kind of figure out what you need to do in order to write and launch kernels that are going to be efficient. And so before we get started, while people are, going through this, I'm going to go ahead and kind of just talk a little bit about, you know, talk a little bit about where we are. And so just kind of get an idea, like, what does the CUDA Python ecosystem look like? And so at NVIDIA, we've had, you know, the CUDA runtime is written in C++. Generally, everything started over on the C++ side. So if you have used any low-level libraries, you've probably used things like Thrust and Cub, or you've used something that's kind of, you know, over on that side of things in order to build your kernels, or you've used, you know, one of the 17 math libraries that's over on the C++ side. But what we've been trying to do over on the Python side is fill in the gaps. And so when you think about all the way down to the hardware, we're going down here all the way to our host runtime. So that's your CUDA runtime that's actually executing on top of your GPU. That's what makes everything possible. Every time that we're launching a kernel, we're interacting with this runtime that sits on top of your GPU. And then as you move up the stack, things get a little bit easier. You're starting to work with your productivity layers. So a lot of people come to GPU computing through PyTorch, which would be kind of at the top of the stack. PyTorch is still built on top of CUDA, so they do have access to CUDA internals all the way from PyTorch. And I've been telling people that, you know, really whatever you're trying to do on the GPU, pick the layer that makes the most sense to you. Worry about your productivity before you start worrying about whether or not you have access to all of the CUDA internals. Start at the top of the stack, as far up the stack as you can. That being said, the best way to really understand CUDA, though, is to go low in the stack. So that's where we're going to be today. And we're really going to stick pretty low down in here, so right on top of the hardware. And you're going to see that interaction between hardware and software as we go through this. And so the big thing to also keep in mind is that, like I was kind of talking about, don't worry so much about which layer you start on, because there is interoperability between all of these different parts. So we have the NumPy array API implemented at all levels here. So whether or not you're working with a GPU array, a Numba array, a CuPy array, a tensor over on the PyTorch side, you still have the same API. And because of that implementation, you're able to move up and down the stack relatively seamlessly. And so things like being able to compile down your kernel with Numba and then pass it into PyTorch, 100% possible, not a problem. And so we actually don't talk about that in that computing hub. I'll show y'all, I do have some tutorials in there that actually go through that if you want to learn more about that. But we're going to stay pretty low level, like I said. So this is where we are. So we have changed the name of this library a couple of times, so just bear with me. It was CUDA.parallel when I put the slide together. In here, you're going to see CUDA.compute is the name of the library, and they actually just changed it yesterday to CUDA.algo. So like, just ignore that. It's all the same library, okay? And it's really the equivalent of like what you would have seen if you are familiar with the C++ stack over on the Cub side. And so that's the library that we're working with. But we're going to look at CUDA.core. So this is right on top of your GPU. And then we're going to talk about CUDA.parallel, which is now CUDA.compute, CUDA.algo. I'm just going to call it all of those things as we go through here. And those are the two that we're going to talk about. As you can see, there's a lot of ground between these two. But the thing to keep in mind, the reason that we're talking about this is going to give you a really good idea of like what is happening on my GPU. And then here, we have a whole collection of kernels that are already implemented on that level that you can call. And so I highly recommend taking advantage of really powerful libraries that are already available out there in order to have to avoid writing your own kernels. We talked a little bit about the CUDA toolkit when you're doing deployment piece of this tutorial just a few minutes ago. This comes with a lot of stuff. So it includes, the NVCC compiler. This is what we use over on the CUDA side. Math libraries. These are the C++ math libraries that are coming with it. Binary utilities, drivers, runtimes, compiler libraries, the core libraries. So that CUDA.algo compute parallel. That is part of the core libraries. It doesn't come in on the Python side. Only the C++ versions come in when you install the CUDA toolkit. And then developer tools. So Insight is really it's the name of the overarching group of developer tools that we have. Unfortunately, we don't have enough time to go in there. But I highly recommend taking a look at that because it will show you, am I getting 100% saturation on my GPU? Do I have, what kind of performance I'm looking for with my kernel? And that's what's going to give you the ability to see like, oh, do I need to tune this? Can I get more performance out of this? And especially if you're using one of the higher level libraries that I was just talking about, you can see whether or not it's worth your time to go to a lower level and try to get more performance out of it. You may not need to. You may not get enough performance out of there. So this is where we're going to stick. And so if you look at CUDA.core, this is what we're really talking about, both the compiler libraries and then the driver plus runtime. And then for the core libraries, like I said, this is the CCCL libraries. And I apologize for this namespace thing. It just is what it is right now. And so those are the two levels that we're going to look at things. And from here, I do want to mention this accelerated computing hub again that Natty also mentioned. I'm so sorry. This is going to be. It's hitting my T-shirt. So I'm never good with the microphones. But if you come out over here, this is what Natty was showing you. Over here in the tutorial section, we actually have quite a few tutorials out here. So there's the accelerated Python. This is the superset actually of all of the Python notebooks that we have available. And there are buttons to open in Colab. So if you want to come back and work with these over in Colab, feel free to. But this tutorial is also available here. It's the second one that's here. It's the 2-hour CUDA Python, CUDA.core CCCL tutorial is the one that we're about to start. So it kind of gives you an idea of what's going on in there. And also, we were just talking about deployment. Keep in mind that there are Docker Compose files available in here, so you can get an idea of what's out there and how to put this together as well. So hopefully you've had enough time to get this up and running. Is everybody here? All good? Anyone not there? All right. So question. Do y'all want to go ahead and take a break now, or do you want to do one of these and then take a break a little bit later? Now? Later?
If we take a break now, would this instance go away?
No. I was going to take a break because I wanted to give y'all enough time to have it actually come up, but it sounds like everybody's got it. But yeah, let's go ahead and take 10 minutes of bio break, water, whatever you got to get, and then we'll dive in here. We got a lot of ground to cover, and I talk real fast, so let's go ahead and get ready.
Okay. And so just as like a really quick background before we get into this, I just want to talk a little bit about like what the GPU is and like why you want to use it, okay? And so the thing to keep in mind is that most of us are familiar with our CPU, maybe not have used our GPU quite so much. It's really helpful, it's a mental model to think of your GPU as being a separate computer away from your CPU, okay? And so like if you think of it that way, they have this one, link between them. And so that's going to be your PCI bus, and that's what's going to move data across from your CPU to your GPU. In a lot of cases, that is the most rate limiting step in GPU computing. Because once it gets over to the GPU side of things, it can just fly. So the architecture, oh wait, okay, go ahead and, I'm sorry, maybe it's here, or maybe not. What happened here? This is not giving me a lot of confidence, I'm sorry. I lost one of my pictures, but it's okay. But basically, once you get over onto the GPU side, you just have a ton of basically really, really, really fast computation. And it's really good at doing parallel processes that are numerically based. Anything that has to do with a string, it's probably going to move a little bit slower because of the variable nature of strings. It doesn't do all that great with if-then-elses. So if you have a lot of branching logic, it's not going to really do all that great with that. Or if you're doing a whole lot of operating system calls. Obviously, your operating system is pretty good on your OS, which is CPU bound, right? And so if you're calling out to your operating system a lot, you're going to probably see some slowdowns there too. That includes print. So I want to make sure people are really clear about that one. So when you're having to move things back and forth, one of the things that we're going to be really careful about and that you're going to see in this tutorial is like, how do we avoid moving things across that PCI bus over and over and over again, making copies? Because that's one of the main reasons people don't get the performance out of their GPU that they're looking for. So I kind of showed you a little bit of a diagram of what the CUDA Python, stack looks like. Obviously, it's a huge ecosystem. But when we talk about what CUDA Python actually is, we really are referring to this low-level piece. And so that's going to be CUDA.core, which is what we're going to talk about here. And that's, your runtime plus your other core functionalities. So that includes like your, core compute libraries. Your bindings. So there are a lot of low-level Python bindings on top of that CUDA API. Like I said, all written in C++. And then Pathfinder, we'll just skip that. And then these are the CCCL libraries. Numba.CUDA is also included in there. That's a different tutorial. If you are interested in Numba.CUDA, there is a tutorial in that in the Accelerated Computing Hub that you can take a look at. We have a lot of materials about Numba out there, and that is really for compiling a subset of Python code, mostly NumPy related, in order to be able to create kernels and then launch them, which actually, by the way, works really, really well with NVMath Python. So I mentioned over on the C++ side, we have about, I think it's like 17, maybe 15, 17 C++ CUDA libraries, math libraries that are out there. So cuBLAS and cuFFT and cu blah, blah, blah. There's a lot of cooing in there. And like on the Python side, we have one. We have NVMath Python. So that's going to give you all the functionality of all of those math libraries. Plus we have native Python support for like FFTs. But the thing that to keep in mind on this one, and why this is such a huge winner, when I was at Supercomputing, I gave a talk on this, and I was talking about how NVMath Python, the reason that you use it is for optimization. And so talking about, like the whole reason you go low level is because you want to get every single tiny itty bitty bit of performance out of your GPU. This has the ability to do kernel fusion, so it's actually going in and it's going to rearrange your compiler code in order to be able to create kernels that are fused together. So if you're calling multiple math kernels, one after the other, a lot of times it's going to return back to your CPU. We want it to stay on the GPU, so we're going to fuse them all together into one giant operation. And the other thing that it has available to you is auto-tuning. And so once you have all of everything fused on there, and it's running really fast that way, it'll auto-tune in order to get that next bump of performance out of it. So I highly recommend checking it out. I'm a huge fan. And so with that, let's go to CUDA.core. So go ahead, also from that beginning thing, click on the CUDA.core devices, streams, and memory. All right. So CUDA.core, this is that module that provides a direct access to the CUDA drivers API, and it's going to give you the maximum amount of control for your GPU programming. The thing to keep in mind on this one is that this is GPU dependent. This is as close as you're going to get to your hardware. So your ability, like what is possible on your hardware, depends on the model of GPU that you bought. So if you're using something that's like an H100, it's going to have different capabilities than if you were to go all the way back to like a T4, something like that, right? And so keep in mind that not everything is available to you depending on which version of GPU you have available and what is in there. As you can imagine, as we're moving through time and we're getting GPUs faster and faster and faster, we're adding more and more shared memory, more pipes to move data, things like that. And as we add more things in there, we get more pin memory and shared memory and different ways to move data around. We're having, we have another thing to control on the low level. Yes?
Why is there the difference that it seems like your number of SMs, your streaming multiprocessors, is more important than your number of CUDA cores? And what's the relationship between the two?
Yeah, that's actually not an easy question anymore, and it's also hardware dependent, actually. Yeah. And so it also depends on what you're trying to program. In some cases, it actually does matter how in the reverse. Oh. And so the thing to keep in mind on there also is that the number of cores that you have on there, just be really careful because of the fact that if you do get to a point where you're almost like getting to the point where you're maxing out on your bandwidth, not your compute, right? And so the number of SMs that you have on there and you're streaming, that's when that becomes like a bigger, that's going to be your rate limiting at that point. So there are different tricks that you can use, by the way, in order to be able to stop that. And so just to make sure that we're all on the same page about vocabulary. Yes?
I think that you may have just segued into my question, but what exactly is a kernel in this context?
Yes, we are about to get to that.
Sorry.
So let's talk about kernels, right? First, there are a couple of things I want to make sure that we're all clear on when I talk about context memory. I'm talking about the execution context in which your kernel is running. Your memory allocation, I want to make sure that we're talking about, I'm going to be talking about loading and freeing memory on your GPU, okay? Kernel compilation, that's when we're going to take our CUDA code and we're going to compile it down into machine code, okay? Synchronization is when we're managing those streams and events. And so synchronization, we have to take care of that in several cases, especially if our GPU is off and running and we want to bring something back over to our CPU. We got to synchronize them up because they don't talk to each other unless we make them talk to each other. And then, but that being said, when I talk about a kernel, it is a function. It is something that's going to run on your GPU. The difference, however, is that a kernel it does not return by value. It has to return in memory over on the GPU side. That's the only way that we're able to move answers across from the GPU to the CPU. We allocate memory for the answer over on the GPU, and we're going to copy it from memory over to your CPU. So it returns nothing. It cannot return anything, okay? Because it's not going to go anywhere. And so that's the thing to kind of keep in mind, but it is specific to your GPU. It will not be portable. If you compile something down and you try to run it on your CPU, it will not work. It is specific to your GPU. All right, so the first thing that we get to do, let's verify that we have this installed. And this should be pretty straightforward, but this is some of the properties that you'll be able to see. So I just want to do this so you can kind of see that we do have that direct access to our GPU. So the things to keep in mind here is, it's giving us our CUDA driver version. If you do run into some driver issues, which happens from time to time, that you need to move up to a different driver, keep that in mind. And then your device UUID and PCI bus, things like that, so you can get information about it. Let's move over to our CUDA concepts. So when I talk about the host, I'm talking about your CPU, When I talk about device, I'm talking about your GPU, okay? And so that is the thing to keep in mind because we do have host and device libraries that are available to you. So both of them fall under the CUDA umbrella, but there are reasons why you want to be able to use and control things on either side, right? And so the other thing, we just talked a little bit about what a kernel is. So that's the function that's going to run on your GPU. The thread is going to be that individual thread of execution. That is the unit of execution on your GPU, okay, which is a little bit different from a CPU thread, by the way. But it is something to keep in mind. Threads are then actually organized into blocks. So that's your group of threads. And then you have blocks that are all going to organize together into a grid. There are warps in between there, but we're not going to talk about warps, okay? And the thing to keep in mind here is that generally what we're going to talk about here is a thread and block execution model here. Moving forward, not to confuse you too much, but when we start moving into tile programming, Qtile was just released last week, so this is the future of CUDA programming. Over on the Qtile side, we're going to be talking about warp level execution. But for now, this tutorial especially, and these lower level things, we're going to be talking about a thread and block. And the thing to keep in mind, by the way, on Qtile is right now it only runs on Blackwell, and that's the only reason I'm not showing it to you. It's a little hard to get access to Blackwells right now. And so let's go ahead and move to this next one. Let's get our device ID. We already know it's 0. We actually saw that in our last cell. We're going to get the device. We're going to set it as current, and then we're going to get the device ID. It should match what we saw above, just showing that everything is working over on our GPU. Let's get some more properties. Here, there is a very good possibility you are on a different GPU than I am, by the way, because we had to kind of move around like which ones people were available or which provider people were able to use. A lot of times I do this on a T4. I am on an L40S on this one. And once again, this is going to change depending on what model of GPU you're using. So once again, those compute capabilities, the higher the number in compute capabilities, the more recent it is, and the more capabilities that are available, more little, wires and tubes and memory and things like that that are available to you. And then of course, our multiprocessor count, number of threads per block. We'll talk about that in a minute. And then also our maximum block dimensions. And this is a really important one because we do, especially at this low level, we have to actually allocate and define how many threads per block we're going to use in order to launch a kernel. And so you can't go out of bounds on this one. The tracebacks at this level in CUDA.core are nasty. And I'm just going to be really, really clear about that. And so try to kind of get an idea of what's going on there, but you're going to see deep down into the driver tracebacks. And so we're going to talk a little bit about error handling through this whole thing because you will run into errors. Okay. Device synchronization. We talked a little bit about, yeah?
I'm sorry. This may be a naive question, but you mentioned earlier that the CPU threads are slightly different from GPU threads. Mm-hmm. Maybe this is not the right time to ask a question, but could you expand on that a little bit?
Yeah, let's do that. I'll talk to you more about that.
Sure.
It just kind of keep in mind that executing on a GPU is different from executing on a CPU, right? And so the way that they're spun and basically collected at the end is just different. Okay. Yeah, just kind of think about that. They're just different pieces of hardware.
I think also is it be reasonable to say you have to worry a lot more about race conditions than you do on a CPU, or maybe not?
It depends. I actually think that you have to deal with race conditions a lot between your GPU running and getting things back over to your CPU more than anything. And that leads to the synchronization thing. You're going to see this in some of our examples. Some places I actually leave it out, but it's a good practice to remember that if you are pulling things back over to your CPU to sync your devices. And so we're just calling to sync here. And here you can see basically all of our GPU operations are going to complete before it comes back to our CPU, and we're calling to a print function. Okay. All right. And so, yeah, when do you want to synchronize this? When you're copying results back from your GPU to your CPU? When you're timing how long your GPU is taking. This is an important one because if you take your timing information before it synchronizes, it's going to come back a lot faster than it actually, because the GPU is just going to keep going. Okay? So they don't talk to each other unless you want it to. And before shutting down your program, because also your GPU can keep going, even after your OS has supposedly ended your program. Okay. So the next one, let's talk a little bit about memory allocation. And so here, same as we've done before, you're going to see a lot of boilerplate code in these, but we're going to import NumPy. We're going to import our device. We're setting our device ID to 0, so that's the only one that we have so far in our environment. Set it to current. Here, we're going to store 1,000 float 32 numbers over on our GPU. So we're going to take the number of bytes. So that's going to be 4 bytes for 32 bits, right? And then we're taking that, we're going to multiply it out. Over on the device, over on the GPU, we're going to allocate that memory. And then now we have memory allocated over on the GPU.
Why didn't you have to call sync for that? Like, I know you're not copying any data back, but how do you know that GPU didn't just say, sure, I'm doing that, and...
Well, I know that it is actually going, I don't have to call sync because, once again, I didn't copy anything over there. It's just an allocation call, which is atomic.
Okay.
But it's a good call because, like I said, there are times where I just leave the sync out. Like, most of the times I have them in there because you are going to see some timing information in here and print statements. But sometimes I just leave them out because I'm just not needed. Anyway.
Question. So I noticed you had already initialized your GPU, right? Why are you doing it again here?
Oh,
Because
this
with
is
the
just
device
best
name-
practice that
Oh,
you
okay.
always have to set your device. Over on the CUDA.core side, everything is explicit.
Because I thought you did it a few cells above.
Oh, I did, yeah.
You just have to do it again.
Yeah, no, it's just in case, like, I skip around these notebooks a lot.
Okay, okay.
So, yeah. But yeah, like I said, you're going to see that boilerplate pop up a lot.
Okay.
Okay, so here we've allocated our memory. Boom, there it is. There's our buffer object. We have a handle to it, and we would be able to use it from our host over to the device. Okay, now let's compile our first kernel. Remember when you signed up for CUDA Python kernel writing? Just kidding. We're going to do some C++. And so over here, we got a C++ kernel here. And this is the thing that you got to keep in mind is that CUDA.core is going to be taking in C++ code in order to be able to do its compilation. If you want to stay in Python, use Numba, or you can use the CCCL libraries, okay? And so from this side, you are going to have to go ahead and set up your just letting it know that this is a void function. Once again, kernels cannot return values, so you cannot have anything returning from it. We're setting it as a global function so that it can be found in the namespace across both host and device. From here, we're just taking finding our index into this, and this is where we get into the threads, the blocks, and then the actual dimensions of the block, right? And so in order for us to figure out the value that we're going to be operating on, we're going to have to explicitly set this. And so you have an index into the number of threads that you have allocated, the number of blocks that you have allocated, and then, so blocks per thread, and then also all the way down into dimensions, or threads per block, sorry. And then from here, so we got our unique ID here. We're going to go ahead and do a boundary check. I already said that it's not like branching logic, not great on the GPU. This, however, is important because nothing's going to stop you from going off the end of your data on the GPU. There's not going to be an out of bounds error or anything like that. So go ahead and make sure that you're within your bounds. We're just doing a simple addition here. Yes, obviously we have addition kernels available to you. You can call this directly from CuPy, or all sorts of places have this already implemented for you. But this is just for demonstration purposes. And then down below, we're going to compile it. So here, you can see I have it actually changed I haven't even run it yet. All this is the compilation step. So all we're going to do here, we are telling it, hey, create a program. We're sending in the source code, telling it what type of code it is, and then we're going to compile it. You see this CUBin here. There are also other ways to compile things down. So CUBin is your CUDA binary version. There's also FATBin. CUBin is going to be 100% specific to this particular compiler, this particular hardware, everything like that. If you do want something that's more portable, you're going to have to do something like a FATBin. Those are fatter, though, by the way. So you are going to end up with a bigger binary. But this is just fine because we're just going to be sending it over to our GPU this one time. And then so let's go ahead and get the kernel. And bam, you have now compiled your first kernel. Woo! Yay! We're all, and now there's more to say. Okay. So from here, then let's run this. Okay. So we talked a little bit, or at least Danny had mentioned that the NumPy and CuPy are very related. CuPy is actually a drop-in replacement for the CUDA version of NumPy. So it has the exact same API, and in fact, you can move between NumPy arrays and CuPy arrays very, very quickly. And it's an easy way to be able to move data over onto your GPU without having to worry about streaming your actual bits over, okay? So we don't have to go all the way down to that level. So what I'm doing here, same thing as before, setting our device. I'm creating a stream. The stream here this is what's going to create our execution steps, okay? And so this is what's going to tell it this instruction goes before this instruction goes before this one. And so it's an execution stream. We're going to prepare our data, so just 1,000 elements. We're going to go ahead and take a range, NumPy arrays. And then I'm going to move them to the GPU here. This is what I'm doing with CuPy, is I'm using it as a way to just transfer my data over. It's an easier way to do it. And so that's all I have to do to move it. And in some cases, I don't recommend actually using it because it gets a little confusing to remember where you are, whether you're dealing with CuPy arrays and NumPy arrays, but they actually do dispatch to each other because they have the same API implemented on both sides. So then what I'm doing here is I'm copying everything over. And then I'm creating an empty array here because I have to put my answer somewhere. Remember, I have a void function. So I have to create the answer space over on the GPU. And that's going to be this empty array here. Here, I'm going to go ahead and set my block size. 256 is a good place to start, by the way. It does have to be a multiple of 32. But unfortunately, there was at one point in time a linear relationship between GPUs and the number of threads per block, and that has since been destroyed. So there is no 100% foolproof way to create this number. So this is a good place to start. 256, 512 are the two numbers that I usually start with in order to be able to do this. I wish I could give you a better answer. It comes up in every single tutorial. It's just the way the world we live in now. So go ahead and set your block size. From here, we're going to go ahead and take the number of blocks needed. So we're looking at the modulo division because even if our data doesn't fit into our blocks perfectly, we're going to have a little bit of extra space there, right? Just to make sure all of it moves over. But we have to allocate by the number of blocks. And so if it takes, extra space, that's what we have to allocate. All right, so we have everything, our launch all configured here. Here, we're going to go ahead and set up the launch config, send that over, and then we're finally going to launch this thing, okay? All right, so then we're moving everything over. It's going to execute. It's going to create our answer over in space. We are syncing in this one in order to make sure that we get everything to complete. And then we're going to move it back over into NumPy on our CPU so that we can look at the answer. So, no surprises, right? We've created our arrays, send them over, execute, and come back. Yes?
So the block size is set as 256.
Uh-huh.
Then I did notice that you had this thread index computation that you're doing. When it's 256, is the indices from 0 to 255, and is that how it is?
Yeah,
And
there's actually a note in the
Oh, sorry.
Oh, no, it's okay. Like, just in case you need to go back for your notes, all of these are available out on that GitHub repository, and there it'll show you the little indexing thing, so you can kind of get a better picture of that. Yeah.
So you said like the block size is like kind of non-standard in some way, and I was just curious about the launch configuration here. It says 4 blocks of 256 threads. Can you parse that and just take the 256? Or is there
So we set this explicitly, right, the 256. We used 4 in order to get 1,000 elements to fit into it. So 256 times 4 is going to give us what, 1,000. 16. So we have some extra space in there because we have to make sure that our data fits into our blocks.
But, sorry, I was kind of going between two things. Further up, we found that at least my GPU has 1,024 max threads per block. Yeah. And so is there a reason to do 256 versus 512, or?
It just kind of depends. Like, I mean, like I said, I wish that I could give you like a definitive answer there. It's just a good place to start. You could use either one. It's fine. And especially for these examples, it wouldn't matter.
Is there a reason why I wouldn't just take the max threads per block?
People always ask that. And like, you know, I think that it more has to do with portability than anything. So people who do want the same code to run on multiple types of GPU that don't have the same capability, you'd want to take that into consideration.
That makes so much sense. Thank you.
Yeah. Yeah.
So it's threads that are like limited by the actual hardware, but then like the way that you're configuring these like blocks and grids maybe is just like problem specific.
Well, it is still constrained by your hardware, but you would want to set it up in a way that allows your data to map efficiently, I guess is the best way to think of it. Does that make sense?
Like how is it, like if you have 1,024 threads like total, right? Like how is it hardware constrained whether you have one block with all of them or 1,024 blocks with one each?
Oh, yeah, no. What, to your point, yeah, as long as it's within the actual capabilities of the GPU,
Gotcha.
honestly, it's probably not going to matter.
Okay.
Yeah. It's more, like I said, portability, making sure things work across different hardware, things like that, right? Because not everything's going to have the same specs. All right. And so here you can kind of get an idea about, you know, basically how it was launched. From here, we actually have, no, let's go ahead and do this one. So let's do an advanced kernel example here. And this one, we've now moved into 2 dimensions, right? So here, instead of, we're going to take over, do matrix multiplication as opposed to handling 1 dimension where we're just taking 2 arrays and adding them together. And so with matrix multiplication, in this case, once again, we're going to create our void function over on the C++ side, send in a pointer to A, a pointer to B, and then the size of, that'll be our space for how everything is actually stored over on the GPU. Where it gets a little bit tricky is that now in order to index into this, we have to look at both rows and columns in order to make sure that we're not running off into no man's land. So when we allocate our data, we want to make sure that we stay within the bounds. But in order to do that, we're taking our block ID, our dimension, and thread index like we did before. So it's the same kind of computation, but we're taking it in 2 dimensions instead of 1. And so here we have to make sure both row and column are within bounds. And then we're going to go ahead and do the multiplication, which is really just a summation. Store the results, take that sum and store the results. And then in this case, we're going to go ahead and launch it just like we did before. Nothing has changed in this one, by the way. You may notice here that I do have the program options is slightly different, just specifying that as C++ 17 is the standard that I'm using on this one. And that one generally, you know, also depends on like what version. We have a lot of people that are on the C++ standards board over at NVIDIA, so they really get into it, but it's a good place to start. And then here we go ahead, send over the source, we're gonna compile it, and then we get the handle to the kernel, and then down below we're gonna we're going to go ahead and launch it. And once again, sync in order to bring everything back over into NumPy, and then we're going to take a look, which is the same thing as a dot product, right? Matrix multiplication, we're going to take the same thing as the dot product and just make sure that they match. Yes?
So it looks like in the C++ code, you're basically loading the entire like buffer of like both of your matrices or both your arrays or whatever into each individual thread. Like, does that mean that each thread has to access like the shared memory of the GPU, and there's not like do the threads have their own individual memory that you're able to just say like, instead of just getting the whole array from the shared memory, like just take these values, like
Oh, no, it's
all
gonna
you do is
get-
just compute and then just write to this one memory space.
No,
It's
that's
like
a
the
really
only
good
time-
question. It's actually only looking at, like, it is actually going to look at parts of it, right? So it is going to parallelize all of that, right? And so you're not, you know, each of those threads is, you have thousands of threads that are going all at the same time over on your GPU. And so you're still indexing based on like that thread that is going to be pulling it from that shared memory where everything is loaded in. But that index is what's going to make sure that it's only computing that portion of it. But since it's a, you know, since we're doing lookups into arrays, I mean, that's a constant time lookup, right? And so like, that's about as fast as you're going to get regardless.
Gotcha.
Right? Hi.
I'm getting an error that program options is not defined when I run that.
Same.
Yeah, so
Oh,
that import
sorry,
statement.
yeah. It's a known bug and we, sorry.
You just have to import program options, yeah.
Don't we have it?
Right there, yeah, import launch config, comma, program options needs to be
Oh,
added.
it's just from there, okay.
Yeah. Sorry about that. Yeah, we're having a lot of fun with our repository right now, and so yeah, several people have.
So that was the case.
And there would be one more error, the function call changes here. So if you go up, Katrina,
Which one?
the way program option, oh, right there, the way program options is called, you don't have to define architecture. Yeah. You can comment out, yeah. Yeah.
Okay. Yeah, and actually that one is a good one because that is a hardware specific thing. When I wrote the tutorial, that was on a T4, and it would take that, and now we're on an L40S, and it was different, right? We had to configure it slightly differently. Yeah, go ahead. Does that pop up for you now? I'm sorry about that.
No, it's all good. I just
Yeah,
looked at the-
we had a little trouble pulling in the latest version of the tutorial. We also cut it down, so, believe it or not. So we lost some of the imports in this whole thing.
I figured there was a star that you tried to convert to the, that was my guess.
Yeah. There was another, I think that it was probably in two pieces before and put together. Like I said, we did a lot of slicing and dicing of this stuff, because this is very much based on the tutorial I gave at GTC DC, just so you know. And all that was a little different, and I had a different time period I could work with. All right, so just real quick, I did want to do some error handling in here, just to make sure that we're really clear about error handling, because especially if you're at this low level, I guarantee you're going to run into some errors. And so out of memory, invalid kernels, device errors, and launch failures are going to be the main ones that you're probably going to run into. And so here you'll kind of get an idea of, you know, what can happen. In this case, I believe all of these are actually going to pass. But let's go ahead and do this. So yeah, in this case, we have actually allocated everything correctly. Everything looks good. But then if you come down to the common error handling problems that I was mentioning, here you'll see really, really quickly, like, yeah, we don't have a device 999, right? We already know that. We already saw that we only had one device. We have memory allocation down here. I'm going to go ahead and I'm going to allocate an impossibly large amount of data over on my GPU, and it's going to give me some problems with that one. I'm going to go ahead and try and give it an invalid kernel with this one where we know that this is bad. This one comes up a lot, by the way, because you may write your C++ kernel over in a C++ IDE that's going to give you all the error handling and everything like that. And then you copy it over to Python, and now it's just a string, right? So you lose all of your great formatting and highlighting and everything like that. And so sometimes that happens, that you just kind of lose it in the transfer. And then also, of course, an invalid launch configuration. So in this case, number of 0 threads is invalid, right? So in this case, we already know that we have to have multiple threads that are already allocated over there. And so just kind of get an idea of like what this looks like, and just you'll see at least the beginning of some of the tracebacks that pop up in here. And so it kind of gives you an idea. The first time I used CUDA.core, I got a traceback that was, it was really funny. The team was like, oh, you can just put it in Slack so we can see what happened. And I was like, no, I can't. That's not going to happen. So just kind of, use your best practices, do, catch things, exception handling, things like that. All right, so if you want to, we could go ahead and maybe compile your first kernel and launch it, or we can move forward to the CCCL libraries, because we don't, let's see, we got an hour and a half, basically. Y'all want to keep moving forward, or you want to take some time to do some exercises? Because this is C++, it'll be a lot more fun to do the exercises in Python. We'll move forward, yes. Excellent. All right. So let's go back to our intro thing. Go ahead and click on this CCCL customizing algorithm piece. And it's going to open this notebook for you. Okay. So remember when I was kind of talking about our ecosystem, I kind of mentioned where we were in the stack. So here we were down at CUDA.core. So we were down at the very lowest level. You saw that you were directly interfacing with the CUDA runtime. You were directly interfacing with your GPU. Everything has to be explicit when you're down at that level, and that's what you experienced. Here, now we're moving up to the accelerated libraries. And so you saw the CUDA toolkit. The C++ accelerated libraries are included. That's part of the CUDA, the core CUDA computation library. So CCCL, that's where that comes from. And so Python versions of these, once again, I apologize for the name changes. It's going to change again. But you'll see here it says it's called CUDA.compute. Like I said, I'm pretty sure yesterday it was changed to algo, but we're going to use these. So CUDA.compute and the CUDA.coop. And so co-op is the one that's used with Numba kernels, by the way. And so I don't cover Numba in this one. Numba has definitely been kind of covered a lot in the past, especially at PyData. There are great tutorials, by the way, if you do want to go out onto YouTube. Obviously, these are all going to be up on the web on YouTube. You can go back and watch this again, anything that's going on. But there are tutorials out there for Numba. From like PyData Global last year, from SciPy, I also did Numba. For even PyData New York last year, we had a really nice tutorial there. So, and the notebooks are out on the Accelerated Computing Hub, so you could even follow along if you want to learn more about Numba. But on this side, we're going to go ahead and stick with the CUDA.compute library. Just trying to do something a little bit different. So we're not doing the same tutorial every time, okay? All right, and so the thing to kind of keep in mind here is that in this case, where you want to go on this spectrum of kernels and what you want to have, available to you really depends on like how much control you really want, right? So CUDA.core, we were at the lowest level of control that you could get at from the Python side. You may need that if you're really going into like raw kernels, or you're trying to use C++ code that you're trying to port to Python, or any of these other use cases. Over on the other side, what we're going to see here, we're going to now move to the high level, and you're going to see how much easier it is to do now that we're going to be moving to the high level. And here, all of that CUDA.core functionality is still under the hood. The paradigm, the execution model has not changed, but you're going to see how much easier it is in order to just call one of the algorithms and set it up and actually get your results back. And so that was the kind of the point here, is like, let's, but I do think that being able to see that low level gives you a very clear picture of how CUDA is doing its job, okay? And so if you understand, once again, that CUDA execution model, that CUDA programming model, those are universal. Everything that has CUDA under the hood is going to use that same paradigm. And so you can pick up these other libraries. You can pick up domain-specific libraries very, very quickly because the concepts are the same. So you'll see these in these examples. But the first thing that we're going to talk about over on the core compute libraries is that there are several different types of algorithms that are available that are very just commonly used. They're common use cases. Let's see if we got these in here. Okay, maybe not. Okay, here they are actually. So some of these parallel algorithms people should be pretty familiar with, like reduce, transform, scan, and sort. Those are all very, very common, different operations that people want to do on a GPU. GPUs are very good at these things for large data sets. So let's look to see how they do these. Just to remind you, what we're looking at here, if you are not familiar with reductions, we're just doing an addition reduction here. So we have our input here. We're going to go ahead and basically, at each level, we take the side-by-side values and we're going to add them together. Do it again, do it again, do it again. And it's a very, very fast way. Obviously, you're going to get logarithmic time instead of linear time in order to be able to make this work. And so that's where your speed up is coming from, on top of the fact that your execution is going to also be able to handle much, much faster, right? All right, so that's what we're doing here. And so let's look at reduce into. So walking through this code here, we're going to go ahead and prepare our inputs and outputs. So same thing you saw before, where I still can't return by value. I'm still in CUDA, right? So even though I'm calling to a kernel that I didn't write, I still have to set it up the same way. So I create my two input arrays. Or I'm sorry, my input array. I'm sorry, this is a reduce. So yeah, our input array here, this is going to be our output array. And so looking at a reduction, right, we're reducing down to one value. That's why this has a size of 1, okay? We only need that one. And then we're initialize the value of the reduction over on the host. So here, instead of all of that boilerplate that we set up, we're just going to call reduce into. We send in our input array, our output. We're going to basically tell it what kind of operation we want to do there. There are different operations that are available. Obviously, there's going to be addition, there's going to be multiplication, there's going to be different mathematical operations that you can define there. We give it the length of our input, so that's not going out of bounds, right? And then we're going to give it the initialized value. And from there, you can see I just put in a verification step in here so you can see that it is in fact correctly doing this. We call it, and that did not work. Let me go ahead and import. I think I skipped something, but import CuPy as CP.
There's a cell.
There's a cell above.
A little.
Yeah, I'm going to go ahead and remove that. Let's, kind of important. So one thing I'm going to do here, I just want to point out to you is like, did you see that pause?
Yeah.
Notice that there was a little pause, okay? And that's the piece that I just wanted to point out to you, is that that is the just-in-time compiling piece right there. So the first time you're calling out, it's going to actually give you that pause because it's doing a real-time compilation step. So the first time you call it, you're going to pay that penalty. You don't have to pay it the second time. So let's go ahead and run it again. And you can kind of see we don't have to pay that again. So it went from 4 seconds down to 4 milliseconds. And that's the kind of thing that you're going to see over and over and over and over again. So if you do run these multiple times, I think there is some timing information in this one. You'll see that pop up from time to time. Okay. Next one, same thing. We're going to use reduce into, but this time we're going to compute the minimum value. So, this is actually this is an exercise. Y'all want to do an exercise? Sure. All right. We're going to set you loose. It's very, very similar, obviously, to the cell above it. Give it a shot. All the documentation, obviously, is online. Let's see what name they have on there. Oh, it does have compute right now. Okay, cool. So you should be able to see everything, the API reference and everything that's available there. But give it a shot. The answers will go through together, but solutions are going to be available here. Just, if you get super unhappy, you can peek. I won't tell. All right, I heard that most people are done. Let's go ahead and look at an answer real quick. So the thing to keep in mind here is that since we are doing a minimum value, the trick here is that we wanted to go ahead and initialize our value to max int to make sure that we're always getting a lower value. If you're trying to find the maximum, the opposite is true. Go ahead and take a very, very low value, right? In order to make sure that you're always getting the higher value. And then same thing as we did before, input, output, the operation kind, we're taking a minimum, the length, make sure we stay in bounds, and then initializing the value, in this case max int, just to make sure. It doesn't necessarily, that's more like a precaution because you don't know what kind of trash is out there or if it has another value that's in there, or, I mean, you just never know what's out there on your GPU. You can get dirty data out there sometimes too. And so it's just a good practice. Question?
So OP kind minimum is not in the docs for OP kind instances.
Oh, that's good to know. Thank you.
So I'll show you later, but I was trying to find it there.
Yeah, ChatGPT thinks it's min, but it's not min.
Do not trust ChatGPT on any of these new libraries. That I just 100% do not listen. Okay? I'm totally serious about this. ChatGPT has not been trained on any of these new libraries. It will give you the wrong answer. Guaranteed. I caught an intern trying to create some stuff. I was like, what is this garbage? It doesn't work. No, just don't do it. We have co-pilots coming out soon that we're training. That'll be available through Insight.
Oh, I see.
But especially since all these libraries are in beta, you're probably going to notice more API changes and more things happening over time. And so training a co-pilot on something that's just about to change is not really going to be very helpful. So we're collecting a huge amount of kernels, things like that, and in order to be able to train the co-pilot. Okay, fantastic. Let's see, custom reduction, sum of even values. I'm actually going to go ahead and we've already done reductions. Let's move on. So moving down to the next one, let's go to scanning. So if you come down to the scanning section, in this case, also called a prefix sum, we're computing a running total of elements. So for each position, it shows the cumulative result up to that point. There are two types of scans here, inclusive and exclusive. So inclusive, obviously it's going to include the current element in that sum. Exclusive does not include the current element in that sum. And obviously there are reasons why you want each one of those. So here's the visual example here. You can see the input, and you can kind of see the difference between the input, the inclusive and the exclusive to kind of get a feel for what those look like. Let's go ahead and give this a shot. Did I skip over the imports? I just want to see what happens. I think we might be okay. All right, so let's go ahead and run this next example. Here we just have our input array. We're going to create our inclusive and our exclusive output arrays and then initialize our value. In this case, we're initializing it to 0. So if you did have a value that you wanted to start from, obviously you can pass it in here. And then going to do our inclusive scan, exclusive scan, and then we have the verify it with our NumPy implementation, just to make sure that we're keeping honest. And execution started. It's moving on. And here, once again, I just want to point out, the 5.75 seconds down to 5 milliseconds. So second time is always faster. But those match. So maximum scan example. So they're not limited to addition. In this one, we're going to use maximum operation in order to find a running maximum value. So in this case, we're not doing any we're just doing comparison as opposed to mathematical operation. Same thing as before, we have our input array. Our output array is going to be empty. We don't have two because we're not doing input inclusive and exclusive. This is just one implementation. And then we do have to define an operation here. So in this case, we are going to define a function maxOp, and this is what has this comparison in there. Okay, so this is what we're defining as our maximum. So if we have a value that's coming in, or two values coming in, if A is greater than B, we're going to return A. Otherwise, we return B. We're going to start with a very small value, kind of like what I showed you before with the max int and the min and things like that. Just want to make sure that we have a really small value in case we have negative numbers. We want to make sure that we're actually getting a maximum. Perform the inclusive scan, and we're going to go ahead and verify with NumPy.
Katrina, there's a question.
Yeah.
What's the difference here? Like, so you defined your own max op, which just, yeah, very, very simply is just like max. But like Python also has a built-in max, but when you use that, it like throws some like closure issues and stuff like that. Like why, like what is that?
It's a kernel. It's the way that we're having to define it. We have to actually use a user-defined kernel that can be compiled down using the CCCL library. So the other one that's available to you works on a CPU, and that's what it's really designed to do. This one, we're making sure that it runs on a GPU. So it just doesn't know how to compile that down.
So it's actually kind of compiling it to C? It's like a, oh, I see.
Yeah. It's also just a really good way to see, I think that it's actually pretty cool because this also kind of shows you that power of being able to send in compiled kernels. These are very simple examples that we're doing here, but you can imagine that in a much more complicated system where you have multiple kernels and all these things like that, and kind of, pulling all your kernels together, and you want to experiment on some kind of crazy data that's coming in from, like, I don't know, your particle accelerator or something like that, right? That passing them in is absolutely fine, right? You haven't lost anything. still works. You're still in Python. You're still able to actually create kernels and pass them around. So there are a lot of different paths to success in CUDA, and we're just kind of trying to show you some of them. Yeah.
So I was trying to do the previous example with the min function, and it didn't work. And it seems like the error message is specifically that there's something special about built-in functions. So no built-in functions can go into those UDFs.
I'm sorry, what was that?
So the just the question before, like, so the maxop works in inclusive scan. The same thing with the reduce into. But like I had to pass up here, like tried to do it with like I have to actually user define a min, right, for reduce into, and this will work. But if I pass it in min, it says complains about like a closure or something.
That's exactly what he was asking about. Yeah, you can't pass in the NumPy version.
So is that just specific to max and min, or is there any like built-in Python function you can't do it?
Yeah. Unless you're using Numba. Numba is what's going to allow you to actually compile down NumPy code down into GPU code.
Gotcha, okay.
Yeah.
So it's not just built-in Python functions, it's also NumPy functions and other things.
Yeah.
Cool.
Yeah.
Would CuPy work in this case?
No, actually it doesn't. Yeah. No, in this context, it's not going to work. All right, merge sort. Do we all remember merge sort from our data structures and algorithms class? Let's see, merge sort. I like this little example here, just in case any of y'all don't remember what merge sort looks like. But in this case, we're basically merging two neighbors together, and this is how we're getting the n log n types instead of n squared, which is generally what we benchmark against over in sorting. So take it, each one. We're going to merge them together. And we just keep going until we actually have a fully merged group of numbers. Let's go faster. Yeah, but the whole idea is that we're sorting, but you can see how this would be highly parallel, right? Where we're able to send this out to multiple threads, multiple processors over on the GPU. So this is what's going to allow us to get, gigs and gigs and gigs of data out over on our GPU. And still be able to, in some ways, it's very much like a reduction. And so this is highly parallel, which is always good for the GPU. And so here we do have this, already implemented. So the thing to kind of keep in mind here, though, is that there are quite a few options in here, obviously. And so the thing, we have our input keys. We're doing a merge sort on key value sorting. Okay, I'm sorry, I missed that part. So in this case, we also want to be able to take those into case we're doing I'm sorry. I think that in the key sorting,
Sorting by keys, right?
yeah, that's what I was trying to figure out, is if it was sorting by keys or values. I think you have the option of doing both.
I might be doing both when the key is the same.
Yeah, in this case, it's definitely sorting by key.
Yep.
I apologize. That's very handy, by the way. That's cool.
Did someone update this from last time? Because I don't remember this.
Right, so I was kind of explaining that the tutorial I gave at GTC DC got ripped up, and this is a Frankenstein version of what I did before. I'm sorry, I just assumed it was the same notebook I used before. So this is a nice little surprise. I really like this. Okay. And apparently, if you just want to sort keys with no corresponding values, you're just going to pass none in here. And so in this case, I guess we just sort by key. Yeah, so it's just the sorted keys values are not taken into consideration on this one. So this exercise here actually does come from mine. And in this case, we're going to sort by the last digit. This is a little bit tricky because one of my examples is no longer in there. But the big thing to keep in mind here is that we want to create a comparison operation. So that's the main thing. In this case, we want to make sure that we're only taking the last digit into consideration when we're doing any kind of comparison. And then the second one is like performing the merge sort itself. And so give it a shot. I mean, okay, you're not implementing it. Here it's just all of the options that you're passing into merge sort. So make sure that you're passing in your operation instead of the predefined.
It looked like to me when we did the max earlier, for these we can have a return for our custom function.
Oh yeah, for your comparison operation you have to.
Yeah, so you can use it in this case.
Yeah, but notice that is in Python, right?
Yeah.
So that's the thing to keep in mind. Yeah, your kernel will not ever return a value.
Yeah. Which is nice to not, then you have to worry about some clever place to put it.
Yeah. Or not so clever. Okay, so for this one, just wanted to show here that the comparison operator, all we're doing is basically taking the two numbers in as input. The only number or only digit that matters is the last one. So that's why we're doing modulo division by 10 in order to only grab that last one. Okay? And so everything else, no matter how long the number is that's coming in, it really just doesn't matter because we're only using that last value. So it's the same comparison that we did before, but only grabbing the last digit. So this should look really, really familiar because it's exactly what we had in the last example. All we're doing is just passing in that comparison operation. Okay?
This would not work with negative numbers though, right?
Negative number. Oh, that's a good point. No, in this case it would be absolute value, right?
Yeah.
Yeah.
Probably would have to extend your comparator to.
Yeah, you would have to change it because it's not going to take that. I don't believe that'll take it into consideration, right? Would it? Yeah. Anyway, so next, moving on, let's go ahead and go back to our next one is radix sort. Radix is always really fun, just to remind everybody what radix sort looks like. In this case, we're actually going to sort by one digit at a time, right? So in that case, you have like an order n k, k being, number of digits. So you kind of get an idea of like what this looks like. And then you have your fully. Isn't sorting grand? And bam, that's how we're getting everything all sorted. So it's taking one digit at a time. So in this one, we have our array coming in, exactly what we saw before. We have an output array, because in this case, we're not actually reducing anything down. We do have to have the entire array size allocated for the answer. And then we're going to pass it in. We do send in the sort order, so you do ascending or descending, depending on which way you want that to go, number of elements. And so it's very much following the pattern that we saw over on the merge sort side. All we're doing is just moving over into radix sort. Okay? And then descending order, you can see exact same thing, just changed it to descending. All right, no surprises there. And so in this case, we also want to do the key value sorting. In this case, we want to take the student IDs. So that's going to be our key, and then the values are going to be the scores. And so much like we saw with merge sort when we were doing key value sorting, it's the same principle here, where we're able to take this by key and value as opposed to just an array of values. And so here, it's also, once again, the exact same way that we called merge sort when we did key value. It's not anything different. And that's sort of just the pattern we're trying to establish here, is that this should look very consistent as you move through the API. Okay, and so now we have sorted. Bam. Okay, so transformations. I just want to, here obviously is a really, really important one. I'm sure all of us have done plenty of transformations where we're just applying a function to each value, right? We want to transform it, we're going to multiply it by 2, we're going to, normalize it, we're going to, whatever we're going to do. We just want to do some sort of operation across all of our numbers here. In this case, once again, we are defining a function. This is defined in Python. Input array, output array, and then we're going to send in that function, and then it'll run it across the entire thing. Obviously, faster ways to do this, by the way. In CuPy, by the way, you could just multiply this by 2. Like, it has the same, NumPy syntax. So, other ways to do this, but for obviously, there are other transformations that you'd probably want to do. Binary transformations, so we want to do a function applies to a user-provided binary operation to pairs of elements from 2 inputs. So in this case, we have our input 1, input 2. We have our 1 output, same size as our 1 and 2. Something to be careful of, make sure that you do have the same size arrays that you're trying to do your operations against. Otherwise, it's gonna throw an error. Perform that binary transformation. So in this case, we're gonna just add these together, and there we go. So, not too exciting. 2 + 7, 8 + 2, etc. So data normalization is probably, I think, one of the more common use cases that you would find for this, especially if you're doing any kind of data science workflow. So trying to just normalize your data in some sort of way. Here we have house prices. We're putting them, we're just moving it over to our GPU. We have our output, so we're going to create an empty array. Calculate the statistics, so we're going to go ahead and get our mean and our standard deviation. Notice we're doing this over on the NumPy side, and we're going to pass it in. We're not doing this over on the CUDA side, although you do know how, so if you wanted to. And then we have our original prices, mean, standard deviation. In order to normalize it, obviously we want to take the price minus the mean, and then we're going to divide it by the standard deviation. And all we're doing here is applying that normalization transformation. So same thing that we saw before, totally calling it the same way, same API, and then we will look at our answer. All right, is that correct?
Do you have more defined grain control in terms of threads and blocks on these, or you just take what it gives you?
Right, so that's actually a really good question, because in the case of something like this, you are using a higher level library. So if you did want to do something like where you really have the control is like any of the functions that you're passing in, right? That's where you could get some more juice out of these. But if you were to use your Insight tools and you noticed that you were like not necessarily getting good utilization of your GPU or something like that, or you're noticing that you're having some like your IO bound or compute bound or something like that, to a certain degree, you are kind of in this world, right? you would have to go in deeper. There are a lot of ways to customize these and pass things in, but you know, a lot of them have been tuned to about as fast as they're going to go. This is, I actually really hate the term ninjas, but our CUDA ninjas have written these and, you know, kind of squeezing every last ounce of performance out of your GPU. Okay. So transformation with iterators for memory efficiency. So the thing to keep in mind with iterators, the reason that you would want to use iterators is that this is going to allow you to do mathematical operations with basically without allocating memory. Iterators are very, very lightweight. They're going to think of them almost as being like a virtual array kind of, you know, construct or temporary array that's going to work in here. This is what's going to give you the, it's not going to store intermediate values. So you notice that before we were allocating our whole array for output, things like that. We don't necessarily have to do that in this case. And so we're able to still move across our data very, very efficiently using an iterator without having, and like we don't have to pay that memory cost every single time. It's extremely memory efficient. And so here we have a squaring function, we have an addition operator. In this one, we're going to do a counting iterator. So all this means is that we're going across our data, basically this 1, 2, 3, 4. Yeah, it's counting is pretty self-explanatory. It's just going 1, 2, 3, 4, whatever. Transform operator, we are passing in the square function, and you can see that we're going to square each value. Here we do have our results, so we are creating an empty array for our results. That doesn't change. We're going to initialize our first value, so starting with 0. And we're going to reduce into. And so in this case, we are sending over the squares iterator. So it's going to move across our data. We pass in our result to make sure that we're grabbing that. Our addition operation, so it's just going to move across. And then we are initializing our value. And then in order to get our result, we're going to grab, so we have to use getters and setters. We're going to go ahead and get the handle to that, and we're going to pull off the first value. The reason that we're doing that is because everything is going to basically end up in that, because we are doing a reduce, is coming down into that one value. Okay? So this does get a little bit tricky. Okay? Our mathematical verification, just to make sure that we are all on the same page here, is that we're moving across each one of our values, right? And so we are counting across here, and then we're also squaring it. And that's how we're end up with this value. And so what's really cool about this though, right? First you're seeing how you're able to layer different mathematical operations on top of each other, which I think is a really, really powerful thing for you to be able to see. But then also you can see that the memory that's actually used for your final result is only about 8 bytes of data. Because we no longer have to, by using these iterators, we've now saved ourselves from having to allocate all of this memory. And we just are able to like pile them on top of each other. Yes?
What's actually happening in the GPU on that? Because like I understand the GPU idea of like you have this huge array, you're applying the same function to multiple bits of portions of the array. I get that. There it just sounds like a for loop that's run really fast. And like I don't think of GPUs for for loops as much as just like you're applying this function across this whole array.
Yeah. I mean, that's really all it is. I mean, it's the same way you would think about doing NumPy computation, right? That we just think in arrays. And so
But
it is.
not an iterator, not an array.
Right, but I see what you're saying. Yeah, this is really, it gets into more like a C++ thinking, a way of thinking about it. I think it's easier for Python people to think in terms of arrays and things like that. But
like what's happening in the GPU?
Yeah. It is actually just moving across like by each thread, yeah. So you're correct. Like it's not, don't think of it as a big for loop, right? That is not what really is happening. Right?
Okay.
We're actually creating a space in our virtual memory, and it's as it's doing its computation, it's using that to store the value. Does that make sense?
I think he's wondering where the parallel part is.
Oh, it's still operating the same way.
Because, I mean, you're not storing them, if you had everything stored and laid out in memory, you could easily just kind of like chomp down on the different pieces of memory. But here you have to be iterating something, but it's got to be a special command that it says like, well, these values are not actually stored in memory, they're kind of like in a command or something.
And I guess maybe I'm not
Heady.
explaining this right, because we're not really iterating over it, right? I mean, it's very similar to like what we're doing in NumPy broadcasting, right? It's very, very similar.
Is that what you're talking about, or is that?
Yeah, I just more theoretical.
Yeah.
You don't need to be able to talk for it, but.
Yeah.
Oh, so the 8 bytes are only in the CPU memory. Like you are expanding out the generator in the GPU. Is maybe what-
No. We're not allocating anything over on the GPU. We're just holding that value basically in special memory. It's letting us access other memory on the GPU. Does that make sense?
Not really, but it's also not that important. Like, I believe you that it works, and I believe you that it's fast and it's not using as much memory on the host. Absolutely, probably not on the GPU.
On the GPU, for sure, you're definitely not using as much. So when we look to see what we're actually doing here, right? 8 bytes, so we're looking at integers. So we're looking at what, 64-bit integers. Over that is a detail of your GPU, where basically we're able to access different parts of the memory of the GPU, and that we're holding it there. And so it is architecture specific, if that makes sense. And so it's also, but it is still computing parallel on your GPU. I'm obviously not getting the right words for you to, like in my mind, I'm trying to like say what I'm seeing in my head right now, and it's not happening.
I can see how you can take that and do mathematical transformations.
Yeah.
And just get the answer. I don't. That looks like a one at a time operation. If that's derailing the tutorial, don't worry about it. I can talk to you later. I'm just curious.
Like trying to see if it actually has something like in here that tells you where it's actually pulling this from. Let me find it for you, because I think if you see how it's actually laid out, it will make a lot of sense. But this is not telling me anything that is going to actually help me. But I mean, yeah, I'm sorry. I'll have to, let me come back to that.
Okay.
Like, sometimes the words don't match what I see in my head. Okay. This is the next thing that we did want to talk about, is custom types. And so in the case that you want to create a custom type, in this case we're going to create a struct. If we were looking at any kind of picture data here, so if we have red, green, blue pixels of values, we're going to use this decorator here in order to create our struct over on the GPU. And so that's what's going to allow us to do this. I mean, obviously, if you get really fancy or whatever, you could do this with key values and things like that. But this is probably just a much more understandable way to do it, and you're not going to pay a penalty by doing it this way. And so when we look at this, all we're trying to do is we have 2 pixels that are coming in. Our Okay, so yeah, we're looking for the highest green intensity. I was just like, why is this only looking at green? So yeah, we want to look at our green pixel, and if it has the higher value, we're going to return it. Otherwise, we get the other one. Okay, so now that we've defined our struct here by using this decorator, down below, we now have our data type information. We have to make sure that we're really clear about what kind of data type that we're looking at here. And then our data with the RGB values that are in here, we're just creating random values in here for the purpose of this explanation or this example. It's not, obviously if you have an image or something like that, that's where you would get your data, okay? We have our output, so we're gonna have our empty space over on the output. And notice once again that we do have this D type that we're passing in here, so we are taking this in like for 3 values when we're passing that over. And that's what we're going to allocate for our output. So let's define the initial value for the reduction. We're going to use 0 because obviously if we're looking for the greatest intensity of green, probably 0 is a pretty safe bet that we're not going to go into negative values or anything like that. And then we're going to do the reduction here. So sending in our RGB data. This is our output array. We're giving it the max value that we've defined up here, our function. Giving it the size. So once again, we're not moving off the end of the array. Okay, so we are doing bounds checking. And then our initial value. So that's the 0, 0, 0 that we've defined here. Okay. So this is just creating some random data, so it's going to look a little weird, but you can see that these are just random values that were put in here. And then the pixel with the greatest green intensity is going to be this one right there. And it's pretty easy to see, red, green, blue. So it's our second value that we're looking at and pulling that out. I actually think that defining your own data types is a little easier to understand than using like the key value stores, by the way. As far as like wanting to like hold intermediary values and things like that, sometimes it's a little bit easier to do it that way. Because it's also a little bit easier to debug if you need to look at what those intermediate values are looking like and if they're doing anything weird. Okay. So let's do a little bit of work with the iterators. I feel like this is out of order. I'm so sorry. This would have been a lot better right before we went through the, multiple iterators at the same time. Example, by the way. So let's go back over here to counting iterators and constant iterators. It's exactly what we saw before, where we're really just going into a sequence, just sequentially 1, 2, 3, 4, 5, 6, 7, on and on and on. And then all we're doing is taking a sum. So we're going to pass in our plus operation. And I'm sorry, just give me 1 second. I'm actually thinking that we might want to. Okay, I apologize. It does seem like this got a little bit out of order, so just bear with me on this one. But going back to what we were talking about with iterators, you can get a better feel for them, I think, by looking at this. We've already looked at the reduce into operation here. We have our iterator that we're creating. We have our output array. We have our initial value. We're going to go ahead and set all this in. Notice right here that we're computing the reduction for 5 input items. I think that, just kind of make sure that we're clear on like what's going on there, because otherwise, it's basically the same thing that we were doing before. We were passing in the length. We're just explicitly saying 5. Okay? Does that make sense?
First 5 elements.
Yeah. Like, and then, why is this not? Over here. So no surprise here is exactly, we have 1, 2, 3, 4, 5, and 15 total. So maybe this makes it a little bit more clear. We didn't allocate anything, right? We have a counting iterator that basically gave us 1, 2, 3, 4, 5 without us having to allocate a range and move it over to the GPU, right? It's just like magic memory, if you want to think of it that way, right? We allocated actually nothing here. We just used the iterator because we don't necessarily always need, we know what a range is going to look like. So maybe that makes it a little bit more clear because we're not necessarily like, see how that's not a for loop? Like,
No, I see
yeah.
that. Like, I see how you can take an array and index anywhere into your constant iterator
Yeah,
and
yeah.
always get your 1 out. And I guess if your counting iterator, oh, we're gonna add your counting iterator to a 1,000 element array, start at 100, you start from counting from 100 with your counting iterator there. I see how you can do that in parallel.
Yeah, yeah.
Okay, I get that.
Okay, cool. Like, I'm like, yeah, I think that does make it a little bit more clear.
Like, it actually makes more sense when you show, wait, and then it doesn't make sense again. It makes sense when you show combining an iterator with a real materialized array. It makes less sense when I think of how the GPU is actually helping you for dealing with 2 iterators in parallel at the same time.
Yeah, I think
In my head.
just think about, like, it hasn't, you did not allocate any memory. This is a very highly optimized way that it's using special memory in order to be able to move across.
Okay.
Yeah. So in essence, it's like a, I don't want to say think of it as an array, but that's kind of what you're doing, right?
I feel like I've derailed it. Don't worry about it.
No, I feel like I'm not explaining this very well. So, we got days to figure this out. We can hash it out over lunch. Okay, next one, constant iterator. So very similarly to like when we're in NumPy, if we use something like 1s or 0s or something to create an array that just has a single value in there, all we're doing here is we have a constant iterator. And we're doing the same thing. So here we have our input array as an array. We are passing that in, but then we have a constant iterator. We are defining this as a 32-bit integer of just 1. So it's the equivalent of being able to do 1s over in NumPy. And so now we also have our empty output array. So we're passing in our CuPy array. We're passing in our iterator that's like a constant array, if you want to think of it that way. We have our output array, and then we're using addition. So in essence, we're adding 1 to each element in that array that we passed in. Okay? Without actually allocating a 1s array, like we did before when we were looking at array addition. Okay? So we've saved that memory. So yeah, 2 plus 1 is 3, 8 plus 1, 9, 9 plus 1, 10, etc., right? Okay, and then once again for the transform iterator here, we just want to take a square of each value in here. We saw in that early one, I think it does make it, I need to move that example down here because this transform operation, before we layer them together, this is really what you need to see. And so we're just taking the square of each thing. So here we're taking a counting iterator and we're going to have a square of each one of those. And then we're creating our output array here. So the only thing that we've allocated is our output array. we've actually just created iterators for the other ones. And so there is no memory allocation. We've saved all of that space on our GPU.
Is it useful to think about them as like virtual arrays? So they behave like
Did I
arrays.
say that? That's what I meant. Just, yeah, exactly.
Like they don't consume memory, but they give you API like you have that.
Exactly. That is exactly what we're talking about. Yeah. But as you can imagine, this is going to save you a lot of space on your GPU. So that's more space for you to move more memory over. So you can transfer more onto your GPU of your data and use iterators to save space, and then it's going to compute faster. Because once again, we're trying to maximize the amount of data that's going across our PCI bus. So we're not paying that penalty every time that we move data from our CPU to our GPU, right? So that's why this is going to be that much faster. Okay, so we have our counting iterator, our transform operator. So we're just going to take 1, 2, 3, 4, 5, however many elements that we have there, and we're going to square each element in there, and then save the output. And we're going to initialize it to 0. Awesome. So yeah, reducing into, so what we've done is we've created, let's use that word, a virtual array that just has 1, 2, 3, 4, 5. A virtual array that has basically where we're going to square each element. So 1 squared is 1, 2 squared is 4, on and on and on. And then we're using reduce into to get one value out where we're taking the sum. So we've layered 3 different things on top of each other in order to get one answer. And it's about as fast as it's going to get. Yeah.
I mean, one of the challenges when you're doing it at the sea level is you've got to make sure that, again, with race conditions and things like this, if you're doing something like this, like the counting iterator and the transform, do you have a guarantee that the counting iterator has finished what it's doing? Or
Oh, in this case, yes, it's handled by the
otherwise they could be
implementation.
running a different.
No, that's a really good point. That is handled by the CCCL library for you. So you don't have to explicitly do that. If you were implementing this yourself in CUDA.core, you would have to sync them for sure.
Okay.
Yeah. Okay. All right, so now we're going to wrap an array with a transform iterator. So in this case, we have the same thing where, except instead of actually, so we do allocate the data, the memory for our array. It's over on our GPU. So it's like CuPy array that's up there on the first one. Then we're creating a iterator where we're transforming this. So we're squaring each element in there, but we're actually still not actually changing anything in place, if that makes sense. This is still going to be that virtual array version of this. And then we create our empty array or initialize our value, but we're also here doing a reduce into, so we'll have one value that comes out. So we've actually explicitly allocated our data here, and it's, our memory here. This is important if you do have something that's not like this other one we were looking at, an iterator and another iterator, right? If we don't have, those are convenience functions, right? If we don't have 1, 2, 3, 4, 5 as like a, a nice value we want to use, most cases we actually have to use like real data that's coming in, right? We can layer on as many iterators as we need to in order to be able to save that memory and then reduce it into a one value. Using the CCCL library. And you see, like, a lot of this power really comes from that ability to be able to, like, put it all together. So we should get the sum of the squares. once again, let's look at I think the only point of this next one is that it was talking about the type annotation as being important here, but we didn't have it in the last one, and it did it correctly. So, oh, I see what's going on. Yeah, in this case, we're looking at floats. Before we were looking at integers. This does actually become important, especially when you're dealing in floats, is making sure that you do have the type annotation in here. Making sure that your floating point numbers align is actually something you do have to keep in mind over on the GPU. So it's a good habit to get into. And so the only difference between this one is that we have actually created, like basically this is the float 32 portion of this one, and we do have a type annotation in here for our square root function. Yes?
How time is scaling compared to size of int array?
I'm sorry, can you repeat that?
The time, if I'm doubling the input vector, the time of execution will be the same?
It should be logarithmic. Yeah, because especially since you're moving into parallel world, it should be logarithmic scaling. So that's why it gets so much faster. And then you can add on top of that just the actual, if you're using a better processor. Right? So like the move from Hopper to Blackwell, for example, that's 100 times, performance gain just by moving to the new processor. And then you add on top of, let's say that we, move our memory really, really smart. We do a little bit of kernel fusion in here. We're making sure that everything is like working correctly. We've already worked out all of the issues over on N-site compute and everything like that. Then at that point, like it goes blazingly fast. And so one of the use cases we actually just recently showed, I think it was for Vera Rubin telescope. We went from, data that took, I believe it was 11 days to process the data down to 4 hours. So that accelerates science quite a bit, obviously. So instead of taking all of this data from the entire southern hemisphere of the world and having to wait until the next day to process it, you can still do it the same night. And then that allows you to point your telescope and track things. So that makes a big difference, I think, when trying to, especially in that kind of use case. Okay, so let's move on to our zip iterator. In this one, I think this is pretty self-explanatory, but all we're doing here is that we're going to take these in and we're going to zip them together. So we have the two arrays coming in, and then we're going to add them together. Okay, next one, we have a min-max. Let's see, we only have 10 minutes left, and so I want to make sure that you actually get a little bit of exercise time on this one. Let's try and go ahead and do this implementation of a running average. And this is kind of what I was talking about before, that I think that sometimes holding intermediary values is actually really, really helpful. So just as kind of a hint when you're coming through this one, you're going to create a struct that's going to be holding your running sum and then the count as well in order for you to be able to implement this really, really fast. I might just chill. But yeah, go ahead and give it a shot. Hopefully we've covered enough in order to be able to do this one. I think you got everything you need in order to do it. And once again, take a peek if you need a hint or anything to get this one going. But like I said, we only have 10 minutes left. I want to make sure that we at least get a little bit of practice. Okay, with 3 minutes left, are we okay to go through this real quick? All right, I want to make sure y'all get out in time for lunch. So here we're creating our type again, so defining a struct. we have our sum and our count. And notice that these are different data types, right? One is float, one is int. In order to get a running average, we're going to have both, right? We have to take our running sum, and we need to know how many elements there are in order to get that average. For the reduce operation, we're going to take our sums and add them together. Other one, create our counts, add those together, right? We're doing a, sorry, just to point out, moving down, we're doing an inclusive scan, and that's one of the reasons why you want to define it that way. And so that we are pulling in both of those together. And so, and then to create the running average, we take our sum, divide by count. That's exactly what we would expect, right? But notice the type annotation here. So this is a type, or sum and count type. It has our float and integer in here, and we are producing a float. And that was kind of like what we were talking about in the last example, is just making sure that you have that type annotation on there, because it can get a little confused in the compiler. Okay, so here we have our iterator. We're creating a zip iterator on our input. So we're going to take these, this is what's allowing us to basically be able to like pull things together. We are creating an output iterator where we're going to transform our data, and that's where we're going to take that running average and compute it. And so by doing this, we're basically moving through each one of these, and we're going to do an inclusive scan. So it's going to take the sum of everything up to and including, and the count of everything up and to including. And then when we have our final answer, we just divide it out, and we get our one running average. So that's how we've parallelized this whole thing. And I think that the hardest thing to kind of keep in mind here is that I just want to point out one of the gotchas here, right? Our output array at the time that we're defining this transform operator is empty, right? And you look at the order of operations, that can be a little bit tricky to understand that we've actually attached this operation onto an empty array. It's not executing at that time. It's executing when we get down into the inclusive scan, okay? And so that's why it does have values in it by the time we get there, okay? And I know that's like, and so once again, taking our input iterator, input-output, or sorry, our output iterator, our reduce operation, which we've already defined up above, our initial value, and then the length to make sure we don't go off the end of our data. And bam, now we have done a actual reduce into. But yeah, I just kind of, one of the reasons I just want to go through this, make sure that you can see like how you can put these on top of each other. And using something like an iterator is obviously, especially for these like little common functions that come up over and over and over again, like count and sum and things like that, it's going to save you from having to allocate and deallocate over on your GPU in order to make it happen. And then you can just keep stacking them up on top of each other. There's actually, like, even on the back end, there's some optimizations that they actually have built into the CCCL function that's going to, like, further optimize your kernels on the back end, depending on how you stack them up. So that's one of the advantages to doing this rather than rolling it your own, because you have all the tools that you saw over on the other side to do it. It's just that this is a much more convenient way. Once you get used to the stacking and order of operations, they're all called the same way. The API is consistent across all of these different functions, whether it's scanning or reducing or anything like that. And then, like I said, you get that performance for free, basically. All right, that's all I got. What are your questions before we call it quits?
Thank you.
I know this is like down in the dirt, and like most Python people like learn GPUs through PyTorch. So I appreciate the fact that y'all stuck with it, because you know, a lot of time, but I do think this is important to understand what's going on underneath, because then you kind of get a better feel for when you look at your higher level code. Even if you're only staying in PyTorch land for everything, you still have a better understanding in your mental model of what is happening on the GPU and how you can look at it. And any of these things that are actually working on your GPU, make sure you're using your Insight tools to look at what's happening. Over in the accelerated computing guide, I do have some materials around that, actually, if you want to take a look, because there are some common things. Like you may notice that, like, oh gosh, I'm having like 50% GPU, you know, utilization. What is going on? It may mean that you have a blocking call. It might mean that you have something that's going on, or you have some data that's getting copied multiple times. And there are a lot of really nice things that come out of this. And so the flow I generally kind of tell people is like use Insight systems to get the end-to-end performance. And from there, you can determine, okay, am I IO bound? Am I compute bound? Am I bandwidth bound? And find all those little areas. But if it is your kernel, then you can go down into Insight Compute and use it to see what your kernel is doing. And inside there, they also just added Numba debugging into there as well. So you can get quite a bit out of those Insight tools. And like I said, stay tuned for the copilots. Those will be part of Insight as well. And they do have VS Code and VS Code integrations in them. All right, so nice. Feel free to, you know, come talk to any of us. We're easy to find. We'll be here. And thank you.
Thank you.